Why is it hard to prove golden ratios link to Fibonacci numbers? Have you ever wondered why the connection between the golden ratio and Fibonacci numbers is so tricky to prove? It might seem simple at first, but the truth is a bit more complicated. Let's break it down. The Fibonacci sequence is formed by adding the two previous numbers together. For example, starting with 0 and 1, we get 1, 2, 3, 5, and so on. This sequence grows in a specific way. On the other hand, the golden ratio, represented by the Greek letter phi, is an irrational number approximately equal to 1.618. It is defined by the equation phi squared equals phi plus 1. Now, here is where things get interesting. As you look at the ratios of consecutive Fibonacci numbers, you will notice that they start to approach the golden ratio as the numbers get larger. However, they never actually equal the golden ratio for any finite Fibonacci numbers. This means that proving the link requires a good grasp of limits and how recursive sequences behave. To establish this connection, mathematicians often use techniques from calculus and algebra. They might solve characteristic equations or apply mathematical induction. This is where the challenge lies. The relationship is not just about finding a straightforward formula. It involves understanding how these sequences behave as they grow. Another layer of complexity is that the golden ratio itself follows a Fibonacci-like recurrence relation. This means it has a continuous aspect that mirrors the discrete Fibonacci sequence. This dual nature adds to the challenge of proving their connection. You might also find the golden ratio in various geometric forms, like golden rectangles and spirals. These shapes relate visually to Fibonacci numbers, but they do not provide a direct numeric proof. For instance, the Fibonacci spiral approximates the golden spiral but is not exactly the same. In nature, art, and architecture, you can see patterns resembling Fibonacci sequences and golden ratio proportions. However, these occurrences are often approximations rather than exact matches. This reflects the mathematical reality that the connection is about approaching limits and proportions, not exact equality. So, proving the link between the golden ratio and Fibonacci numbers is challenging because it involves understanding limits in recursive sequences, the properties of irrational numbers, and the difference between exact equality and approximation. This makes the relationship both fascinating and rich for anyone interested in the world of numbers and their meanings.